Hi, I'm Neil Cooper, a distance student in the supply chain class. You guys probably haven't seen me, but I've been watching the videos and paying attention and doing the homework and cases and whatnot. It's been a great course. So, here today to introduce and discuss the aerospace implications of 3D printing. My group consists of me, myself, Eric, Stephen Chi, and Annie Sun. We've been working together for quite a while on this report, and hope you enjoy it. So I'm going to talk about an introduction to aerospace. Eric's going to talk about prototype design, and he's going to talk about inventory management. Stephen is going to talk about the market analysis and the future of 3D printing, and the conclusion. So 3D printing. It's a relatively new technology. It's not terribly new, but it started to come out in the 80s, but it's really picked up in the last few years. There's a Wikipedia definition. It's there. I'm not going to bore you with it, but it's quite precise. The easy definition, which seems to be cut off by the template, is you're printing objects in thin layers using plastic or metal. So one layer at a time, and they stack up like pieces of salami to give you a part. And you can see something over here that was 3D printed, and kind of what a 3D printer looks like. So there's multiple different types of 3D printers, going from a couple $100s all the way up to millions. And to a certain extent, you get what you pay for. Now there's some branding implications, but you just currently you can't really get a good 3D printer for a low cost for metal. You're going to pay about $30,000 or more for it. But the materials you can print with those are quite impressive materials. You can print stainless steel, Inconel, nickel, coke, which is cobalt and chromium, titanium, gold or silver, and there's a bunch of others. You can print various grades of these. You can print some really, really strong parts. You can print parts that are designed to fail in certain ways. You can print parts that are strong in certain ways. You can do a lot of things. And the resolution is less than 0.2 millimeters per layer. So you can get some pretty decent resolutions out of these. There may be some machining required, depending on the part, to get a very flat surface or something of that nature. But for a lot of parts, you really don't need that except for a couple places. So that's where 3D printing really shines. On the plastic side of things, you can get a printer anywhere from $20,000 down to about $200. So any of you in the class could buy a 3D printer if you wanted to. There's a little bit of a learning curve there, but it's not terrible. There's various materials you can print in: ABS plastic, PLA, which is a plant-based plastic. It's biodegradable, environmentally friendly, and all that good stuff. It's also fairly strong, but it's brittle. Nylon, which is tough. Polycarbonate, which is incredibly tough. And you can get very good resolutions. For that, you're looking more at plastic parts like trinkets and things like that, or brackets, or things that really don't need to be metal. There's a lot of parts that don't need to be metal. You can also do prototyping and one-offs and print things that you don't need. In college, I was on a formula card team, Formula SAE, and we made our intake manifold by 3D printing, and we used it on our race car. It was great. We were able to get exactly what we wanted, and it wasn't a part that was expected to last a very long time, just a season or two, but it worked great. I mean, the material resistance is good. So there's various real-world implications, and we're still trying to find that out. So yes, Stephen will probably talk more about that in the later slides. So some 3D printers in action. So let's start with the plastic one because it's more simple. This is actually my 3D printer that I have personally. It's not tuned completely well, but it's good enough to print things. I haven't had a whole lot of time to work with it. But here I'm printing a cookie cutter for my girlfriend. So this is what it does. It prints layer by layer, and then it moves up a little bit, and then it prints some more. But once you get to the metal printers, then things get a lot more complicated. This is one that prints metal. And you'll see, it's kind of a long video. I'm going to skip through it a little bit. But here's the print head. As you can see, it's quite complicated. And what happens is the metal powder comes through these tubes and gets injected. It's a very fine powder. And then it goes into the path of a laser beam. And what that does is it deposits it. So here's a couple machines. This is a very advanced machine, but it's printing what looks like a tube attached to a flange, and it has all of these degrees of freedom, so it can print on any angle it needs to. It's so you can get the right material thicknesses and the right um, density of the part. You have to worry a little bit about parts having voids and inclusions, but a process like this will help you on that. So for aerospace implications is where it really shines. You can get the supply chain for aerospace requires low volume productions, high precision, lowest weight possible, and high strength. So you can get these through designing parts that are strong, such as this one here on the top right. I hope you can see my mouse, but just in case. You can get it, but that gets expensive and heavy. So airplanes need to be as light as possible. So to manufacture something like its friend right next to it would be almost impossible via traditional manufacturing from a billet. So you could cast the part like that, but a cast part might not give you the strength required. So you really would be requiring a heavy part or extensive machining or very odd manufacturing practice. But with a 3D printer, you can print the parts one after another, and with minimal cleanup and just, make them. So you can also print parts like the other two, which would be incredibly expensive to manufacture, but are optimized for weight and space and things like that. It's basically because it's an additive process instead of a subtractive process. So you start with nothing and you add material versus starting with a big chunk of material and removing material, where certain parts are conductive to one process or another. So you can get lower weight parts with the same strength because you can core out areas that are not important. This requires extensive FEA analysis, but you can get a lot lighter parts at a lower cost because you don't need to do the post-process machining, such as you would if you had the part and then you need to cut a whole bunch of holes in it to take weight out. You do batch of one production, which is great. We'll talk about that in a little bit, and that will be, that's really attractive to certain industries where you don't hold a lot of spare parts. You can do very strong material strength because the alloys here are super alloys and they're very, very strong. And the reason you're allowed to do that is there's a lot less waste because you're not starting with a big chunk of material and coring it down. There's very little waste, so you can save a lot of money and up your alloy. You can also produce non-manufactured parts. So if you look at this part here, cutting this pocket in here, but again, I hope you really can see the mouse. But there's certain areas of the part on the top right that you wouldn't be able to make without a 3D printer. So that's me. I'm gonna kick it up to the